Think for a moment about all the lists you encounter every day. A grocery list scribbled on a notepad, maybe, or the guest list for a party, even just a mental rundown of your to-dos. Lists are just such a fundamental way we organize information, right?
They really are.
Well, in this deep dive, we're going to take a surprisingly deep look at these seemingly simple lists, but, from the perspective of computer science.
Exactly. That everyday list you're making is actually a really powerful idea in the world of computing called a data structure. Our sources today explore these lists not just as like collections, but as structures with specific ways of organizing and working with information.
Ah, okay.
We'll be looking at how these structures are built and the trade-offs involved in different approaches.
So, our mission today is to really get to grips with the core concepts of lists as data structures. We'll be digging into the different ways they can be put together. Think of using building blocks versus maybe tying things together and what the advantages and disadvantages of each method are.
Sounds like a plan.
Okay, let's unpack this. In the context of computer science, what exactly is a list?
Well, at its core, a list is a collection of items. And crucially, these items are usually of the same kind, like a list of your favorite songs or maybe a list of high scores in a game, as our source points out.
Okay.
But what makes it a list and not just a random jumble of things is that the order of these items is significant. It's an ordered sequence.
That makes perfect sense. The order matters. Our source even gives us a little example. A3, A1, A2, A4.
Right.
Even though it contains the same four A elements as, say, A1, A2, A3, A4, the different order makes it a completely different list in the eyes of a computer.
Exactly. That order is key.
So once we have these ordered collections, what kind of things can we actually do with them?
That brings us to what our source calls useful operations. These are the common actions you'd want to perform to manage and interact with the data in your lists. Think about things like create list. Pretty straightforward. That's how you get an empty list to start with.
Right. Makes sense.
Then there's copy, which lets you make an exact duplicate of an existing list. And clear, again, very straightforward. It just empties the list completely.
Right. Okay. Those seem like the basic setup tools. What about when we want to actually, add or remove things?
Good question. That's where we get into operations like insert X. This is how you add a new item, represented by X, into the list at a specific spot. Now, that question mark in the source is important.
Oh, yeah. Why is that?
Because it points out that there isn't just one way to say where in the list you want to put the new item. There are kind of two main ways to define that position.
Ah, like different ways to point to a location.
Exactly. The first way, and one you might be familiar with from things like, spreadsheets, is using an index, essentially a number that tells you the position of an item. Slot 0, slot 1, slot 2, and so on.
Okay, yeah.
So you could say insert X at index 3, or give me the item at index number 5. The other way is using what's called a current marker, almost like having a bookmark that remembers your place in the list.
Okay, I can visualize that bookmark idea. Like, I am currently here in the list.
Precisely.
So if you're using this current marker, how do you actually move it? How do you navigate through the list to find the right spot?
Right. Well, that's where the source introduces 4 more handy methods. Start, which moves your current marker right to the beginning of the list.
Yeah.
Tail, which jumps it to the very end. Next, which shifts it one position forward and back, which moves it one position backward. Think of it like navigating a playlist with next and previous buttons,
Got it. Okay, so index-based positioning is like jumping directly to track number 5 on an album, while the current marker is more like using the skip forward or skip back buttons.
That's a great analogy, yeah.
Okay. What other operations are common for lists then?
Well, we also have remove, which does what it says, deletes an item at a given location. Again, that location can be specified either by an index or by the current marker. Then there's get, which lets you retrieve the item at a specific location without actually taking it out of the list. Just look at it.
Right, just peek at it.
Exactly.
Yeah.
Update X allows you to change the item at a particular position to a new value. X, find X, is how you check if a specific item X even exists within the list.
Like a search function.
Basically, yeah. And finally, length simply tells you how many items are currently in the list. Pretty essential.
Okay, that gives us a good toolkit for working with lists. Now, the source talks about how we can actually build these lists inside a computer using something called an array. How does that work?
Right. So imagine an array as a row of boxes, all sitting right next to each other in the computer's memory. It's a contiguous block.
Okay.
When you use an array to hold your list, Each item in your list gets its own box in this continuous row. Our source gives an example of a list containing the numbers 2, 6, 8, 7, 1, and shows how they'd be arranged in these adjacent memory locations.
So 2 in the first box, 6 in the next, 8 after that.
Exactly. It also mentions a current position, which is like our bookmark, maybe pointing at the box with the 8 in it and a size, which tells us how many boxes are actually being used for our list. Because the row of boxes, the array itself, might be longer than the number of items we currently have stored.
Right, so the array might have some empty slots at the end, just in case.
Precisely. Room to grow, potentially.
Okay. And how do those operations we just talked about play out when our list is stored in this kind of array structure? Let's take adding a new item, the add operation, for example. What happens then?
Good question. The source illustrates this really well. It shows what happens when you add the number 9 to that list. 2, 6, 8, 7, 1. When our current position, our bookmark, is at index 3, which holds the value 8.
Okay, so we want to insert 9 right after the 8.
Well, the source describes add inserting at the current position, pushing the current item and subsequent items to the right. So to make space for the 9 men at index 3, you essentially have to nudge the 8 men, the 7, and the 1 position over to the right.
Oh.
So the 1 gets moved into the next box. The 7 moves where the 1 was. The 8 moves where the 7 was. Only then is there an empty box at index 3 where the 9 can be placed.
Wow.
And the current marker then moves to point to this newly inserted 9. It's a bit like making space for someone in a crowded row at the movies. Everyone to the right has to shift down 1 seat.
Wow. Okay, so inserting something in the middle of an array-based list can involve quite a bit of shuffling around behind the scenes. That seems potentially slow.
It definitely can be,
Yep.
especially for large lists.
What about moving to the next item, the next operation? Is that simpler?
Oh yeah, that's much simpler. The next operation just moves our current pointer to the next box in the array, assuming we haven't reached the end of our active list items. It's a direct jump to the adjacent memory location. Very fast.
Okay. And what about removing an item, the remove operation, more shuffling?
Yep, afraid so. Removing an item is kind of like the reverse of adding. If you remove the item at our current index, you create an empty box in the middle of the row.
A gap.
Exactly. To keep everything nicely packed together in the array, all the items to the right of the removed item need to slide 1 position to the left, filling in that gap.
Okay. More shifting. It feels like arrays involve a lot of shifting for inserts and removes in the middle. What about finding a specific item using the findX operation? How does the computer locate it in an array-based list?
Well, the findX operation usually involves checking each item in the array, one by one, starting from the beginning, until you either find the item you're looking for or you hit the end of the list.
Just a linear scan.
Pretty much.
Right.
If you do find it, the current pointer is then updated to point to that location. The source even shows some simplified code for this. It just loops through the array, checks each element, and stops if it finds a match. It's like scanning a bookshelf title by title until you spot the book you want.
Makes sense. And the other operations like get, update, length, and moving the current pointer with back, start, and end, how do they work with arrays? Are they shifty too?
No, most of these are actually quite direct and efficient with arrays. Get simply grabs the item at the current index, you know exactly which box to look in. Update X replaces whatever's at the current index with X, again, direct access.
Right.
Length just tells you the size, how many items are in our active list within the array. That's usually stored separately. And the current pointer adjustments, start, end, are just simple movements to different index positions in the array. Because everything is in a known consecutive location, these tend to be very quick operations.
Okay, so the quick access to any position via index is a big plus for arrays, but inserting or deleting in the middle, maybe not so much because of the shifting.
That's a very good summary of the trade-off, yeah.
So we've seen how arrays can be used, but what about how efficient these operations are in like a more formal sense? The source touches on time complexity. What's important for us to understand about that?
Right. Time complexity is basically a way of talking about how the time it takes for an operation to complete changes as the list gets bigger. Yeah. Does it stay fast? Does it get slower? How much slower?
Okay.
Think of it like this. If you have a very long line of people, some tasks might take much longer, depending on where in the line you're working. For the add operation in an array-based list, the worst-case scenario is if you have to insert something at the very beginning, right?
Because everyone has to move.
Exactly. Everyone behind it has to shift 1 spot over. If the list has n items, you might have to move all n of them. On average, though, if you're inserting somewhere randomly in the middle, you'd expect to shift roughly half the elements.
Okay.
Now, What do you think the best case would be for adding?
Hmm. Best case. Maybe it's you're adding to the very end and there's already an empty slot waiting in the array. Then no one needs to move.
Perfect. Exactly. No shifting needed, so it's very quick, essentially constant time. Okay, what about taking someone out of the line, the remove operation?
Hmm.
Where would that cause the most disruption, the worst case?
I'd guess taking someone from the front again, right? Because everyone behind them has to shuffle forward to close the gap.
Spot on. That's the worst case for removal
Hmm.
and the best case.
Taking someone from the very end, then no gap is created in the middle.
You've got it. And again, the average case for removal from somewhere in the middle involves shifting about half the remaining elements, similar to insertion. Now, what about finding someone in the line, the find X operation? Worst case.
Worst case would be if the person isn't in the line at all, or maybe if they're right at the very end. You'd have to check every single person before you find them or give up.
Precisely. You might have to look through the entire list. Best case.
They're the very first person you look at, found them immediately.
Right again. And the average case would likely involve checking around half the line before you find them, statistically speaking.
Okay. Now, the source mentioned that other operations like get and update are often one step. What does that imply about their efficiency as the list grows?
It sounds like they're saying those operations take roughly the same amount of time, no matter how long the list is. Like getting the person at position 5 is just as quick whether there are 10 people in a line or 1,000.
Ah, because you can just jump straight to position 5 using the index.
Exactly. Operations like just look at that specific spot, update, just change the item at that spot, length, just check the stored size, and moving the current pointer using indices are usually very fast. They don't depend heavily on the size of the list because you know exactly where to go in that contiguous memory block. They're typically considered constant time, or O1 in complexity terms.
Right, because you have that direct index access in the contiguous block of memory. Okay, so that's how lists can be built using arrays.